All right, let's talk about vectors. Here's a quick look at the table of contents for this video. So if you're looking for one of these specific topics, you can go ahead and navigate straight to that chapter of the video. So we're going to dive in with the first part right here. Let's talk about the definition of a vector. So a vector is defined as a quantity that has magnitude and direction. And we can see how that might be useful, right? If I told you that I'm in San Francisco and I'm about to travel 2,500 miles, well, you know how far I'm going to travel. You know the magnitude, but you don't know if I'm going to Hawaii or New York or Guatemala, right? But if I give it a direction, if I say I'm about to travel 2,500 miles due east, well, now you know I'm going to the East Coast, right? Because you know that I'm traveling 2,500 miles, you know the magnitude, and you know I'm going due east, the direction. Right, so that's one application of a vector. There are many, many useful applications of vectors, and we'll look at some of those in the next video. For this video, we want to describe the fundamental properties of vectors and how to work with them. So if we look at some of the fundamental properties, a vector can be described as a directed line segment. So let's piece that apart a little bit. So here, for example, is a line segment, right? So it's not a full line. It's finite. It has a beginning and an end. And as a matter of fact, we're going to define this as it moves from an initial point toward a terminal point. Right, so we have an initial point and a terminal point, and it's a directed line segment, so it's going to have an arrow on it. So this is what a vector looks like. It's a line segment that has an arrow on it. And all the parts of the vector are kind of baked right into the drawing of the vector, right? The arrow indicates the direction of the vector, and then the length of the line indicates its magnitude, right? So when we look at vectors graphed, we're going to look at the length of the line as indicating the magnitude of that vector. Now, when we notate vectors, we can do this in a couple ways, right? So a lot of times you'll see a lowercase letter with a little half arrow on top of it. So this is saying this thing that we're looking at is a vector. So for example, I might call this vector V. Right, and so that would be vector V. You can also, in some textbooks, they'll just use bold font, so lowercase letter with bold font. That will indicate that thing is a vector. You can also see if they're like for some more specific detail. Let's say, for example, that this initial point right here is called point P, and this terminal point over here is called point Q, then you can see vectors sometimes written as PQ, so the line segment PQ with that little half arrow on top of it. And that indicates that not only is this a vector, but that the vector is traveling from point P toward point Q. Okay, so the direction of the vector is also very important because when we analyze vectors, we can look at them in two different ways. We can look at positive vectors, right? And positive vectors, we're going to travel along the vector from the initial point toward the terminal point. So from initial toward terminal. And then if we have a negative vector, we're going to travel along that vector from the terminal point toward the initial point, right? And the difference between these two, let's talk about what's similar between them first. So in either case, the vector just exists as the vector, right? So with this example here, the vector is from initial point P toward terminal point Q, right? But when we travel along the vector, and that's a lot of how we're going to talk about vectors, how do we travel along the vector? If it's a positive vector, we're traveling from initial toward the terminal, so the same direction that the vector naturally exists. If we're observing the negative vector, we're going to travel from the terminal point toward the initial point. So the vector still exists as it is, initial to terminal, but we can observe it as a negative vector if we travel from the terminal toward the initial. And that'll make more sense as we get into some of the examples of adding and subtracting vectors. So let's go ahead and jump into that now. Let's talk about adding and subtracting vectors geometrically. So we'll be doing this geometrically, and then a little bit later, we'll do it algebraically. So what does it mean to add and subtract vectors geometrically? Well, we're basically just talking about graphing the vectors, right? So we're going to graph the vectors, but we're going to graph them one at a time because we're going to be adding two or more vectors together. And when we do it, we just want to line them up from tip to tail, right? And that'll make more sense in a second when we look at an example. But when we graph the vectors, we're just stacking them from one to the next. So for example, let's look at these two vectors here. So here in this example, we're given the following information. So this is just given to us that here's vector v, right? We have an initial point and a terminal point, and then over here is vector w. So we have our initial point and our terminal point. And what we're going to be asked to do here is first we want to add the vectors together. So that in this first example, we're going to find vector v plus vector w. And then in the second example, we're going to subtract them. So vector v minus vector w. So when we graphically add them or geometrically add them, we're just going to stack them tip to tail. So here's what I mean by that. First, let's graph vector v. And so we want to analyze how do we travel along this vector. Well, since we're looking at the positive vector, vector v, we're going to go from the initial point toward the terminal point. And kind of like most things that we do in the xy plane, we're really bad at moving at angles, but we're really good at moving strictly horizontally and strictly vertically. So that's how we're going to observe this. We're going to go from the initial point to the terminal point. We have to go to the right 1, 2, 3, 4, and then up 1, 2, 3. So when I graph this vector down below, I can start anywhere I want to. Notice there are no xy axes here. I can start anywhere I want to. And as long as once I choose an initial point, from there I go for vector v to the right 1, 2, 3, 4, and up 1, 2, 3, and then plot that line. Let me darken that a little bit. Let's try that one more time. There is vector v, and then it's a vector, so I want to indicate its direction. So there is vector v, right? And actually, I do want to move this because I was just looking at vector w, and I'm going to have to add that. So let me just move that down here. So 1, 2, 3, 4 to the right, and 1, 2, 3 up. And there is vector v. I'm just going to go ahead and label that as vector v. Okay, so there's vector v. Now I'm going to add vector w to this. So this is what I mean by tip to tail, right? So here's the tip of vector v, and to that I want to add the tail of vector w and then travel along this vector. So positive vector w from the initial point to the terminal point goes left 2, up 1, right? So I'm going to start this vector where I ended the last vector. So I'm going to start right here. I'm going to go 2 to the left and up 1. So here we go. So 2 to the left and up 1. And then I'm going to indicate that is the direction that we're traveling along this vector, and I'll label that vector w. So it looks just like that. I kind of just copied and pasted it, right? And so now we've added these two vectors together. Now, when we look at the result, so this says find v plus w. So when we look at the result of this vector, what we're really looking at is we always want to go, no matter how many vectors we're adding together, we always want to start at the very first starting point. So whichever vector we graphed first, this is where we're going to start for our resultant vector, and then we're going to move toward the final end point. So the initial point, the very first initial point, straight to the very final terminal point. So initial point to terminal point, right? No matter how many vectors there are, we do this. And so now we're going to go from the initial point toward the terminal point, and we'll indicate this direction, and then we can label this as vector v plus vector w. So this is what's called a resultant vector, right? So I'll just write that down. This is a resultant vector because it's the result of adding vectors v and w together. All right, so then let's look at vector v minus vector w. And what I would recommend for these is not thinking about the negative vector, but thinking about plus and minus signs as indicating which direction do we travel along the vector. So let's go ahead and graph these. So first we'll start with positive v. So that's indicating to us that we want to move from initial to terminal. So we'll go to the right 4 and up 3 for this. So we'll go to the right 1, 2, 3, 4 and up 1, 2, 3. So there's vector v. I'll go ahead and label that vector v. And now we're going to subtract vector w, but the way I'm going to think about this is it's a negative vector. So I'm going to analyze this in terms of traveling backwards along the vector. So I'm going to go from the terminal point toward the initial point. And in order to do that, I'm going to need to go down 1 and right 3, right? So that's going to be the negative vector w. So down 1, right 3. So from where I ended the last vector, I'm going to go down 1, I said 3, didn't I? To the right 2. Down 1 to the right 2. and then I'll put the arrow. And now when I label this, I'm just going to label this vector negative w, right? Because we took vector w and we went backwards along its travel. Okay, so now to find my resultant vector, I go to the very first initial point. So this is where I started. And then I go to the very last terminal point, and then I connect those two dots. So that's the thing about vectors, is vectors don't care about the journey to get there. They only care about the end result, right? They care about where did we start and where did we end. And so here is vector v minus vector w, and we've just added the vectors geometrically and subtracted the vectors geometrically. Cool, so that's how that works. And we do want to keep in mind that the direction of travel is so important with vectors. So let's look at this scenario, for example. So think about this for a second. So true or false, vector m plus vector n equals vector o. So think about that for a second, and you go ahead and decide true or false. And the answer is, this is false. So this is a false statement, because if we look at what's actually happening here, this says, and let's follow the direction of movement. So this says positive vector m, so we're starting at the initial point and moving toward the terminal point. So there's positive vector m, plus vector n, so we're moving in the positive direction from the initial toward the terminal, is equal to vector o. And here's where things fall apart, because looking at these two arrows, this indicates that our resultant vector should move from the initial point over here toward the terminal point over here. So it would move in this direction. But that's not what vector o is doing, right? Let me get those things out of there. We can see that vector o is actually moving in the opposite direction. So that's what makes this a false statement, is that this is not traveling in the correct direction. Instead, if we wanted to make this statement true, we could say that vector m plus vector n is equal to negative vector o, right? Because the negative direction of travel along o would be from the terminal point over here toward the initial point, and that's how we would connect vector m plus vector n. All right, cool. Next, let's talk about scalar multiples. So scalar multiples is really just a way of saying take the vector that already exists, and we're just going to scale it up or down, right? So this is just scaling a vector up or down by some quantity, by some multiple, right? So we're going to scale the vectors up and down. And I think the best way to look at this is through an example. So let's look at this example. Let's say that we're given the following information, right? So this is given to us. So we have vector m and vector n, and then let's say that we're asked to find 2m minus 3n. Well, one way we could do this is to sketch vector m once and then sketch it again, and that would give us 2m, right? But that's not going to be the most efficient way to go about this. Instead, let's go back to that idea of we're analyzing the direction of travel, right? And then I'm just going to scale it up by whatever this scalar multiple is. So here's what I mean by that. For vector m, to sketch vector m, looking at that, we're going to go from the initial to the terminal, so to the right 4 and down 1. But if I want to scale that up by a factor of 2, I'm just going to multiply those two directions by 2. So instead of right 4, down 1, I'm going to go to the right 8 and down 2. So if we look at that, that's going to be, I'll start here. I'm going to go to the right 1, 2, 3, 4, 5, 6, 7, 8, and down 2. So down 1, 2. And now that is going to represent vector 2m. So I'm just going to label that. This is vector 2m. And now we want to subtract vector 3n. So I'm going to do two things at once here. Number one, I want to analyze the direction of travel. So I want to go from the terminal point to the initial point, and I want to multiply that travel by a factor of 3. So for negative vector n, we're going to go to the left 2 and down 1, but if we're scaling that up by 3, we're going to go to the left 6 and down 3. So from this terminal point here, I'm going to go to the left 6, so 1, 2, 3, oops, let me get that other tool. There we go. So to the left, 1, 2, 3, 4, 5, 6, and then down 1, 2, 3. So there's where that one ends, and I want to put my arrow here to indicate the direction of travel, and I'm going to label this as negative 3n. So that's vector negative 3n. And now graphing our resultant vector, let me change the color here. Graphing our resultant vector, we go from the initial point toward the terminal point, and there it is right there. So I'll go ahead and just label that vector. That's 2m, minus 3n. That's that resultant vector. And that's how we sketch kind of multiple things together there. We did scalar multiples and we subtracted the two vectors. Okay, cool. So let's throw it into a little bit more complicated diagram. So here we have a few vectors. We have 4 different vectors here, and we're asked this question: does a plus 2b minus 4c equal d? And the way that we can solve this is, let's just go ahead and graph each of these vectors with their scalar multiples. So I'm just going to graph it over here on the side. I'm going to start like right here, for example, and first thing I want to do is sketch vector A. So I'm going to look at that and I'm going to go, okay, for vector A, we go to the right 1, 2, 3, 4, and up 2. So I can start anywhere I want over here and then just go to the right 1. Oops, let me get that other tool again. So we're going to go to the right 1, 2, 3, 4, and up 1, 2, and put my arrow, and I'll label that. That's vector A. All right, now I want to add to that vector 2b. So I'm going to look at b and go to the right 2 and down 3, but I want to scale it up by 2. So I'm going to go to the right 4 and down 6. So to the right 1, 2, 3, 4, down 1, 2, 3, 4, 5, 6. And there's vector 2b. So I'll label that. That's 2b. And now I want to subtract 4c. So I'm going to move backwards along c and multiply it by 4. So moving backwards along c, we go to the left 3. But if I multiply that by 4, I'm going to go to the left by 12. So starting right here, I'm going to go to the left 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Almost running into this other vector diagram, but that's okay. So there's that, and I will label that vector negative 4c. All right, so that's everything on the left side of the equation. So that's that whole thing graphed. And now I just want to analyze, is that equal to vector d? So let's see. So I'm going to look at vector d, and I want to know, is this equivalent? So I'm going to put it on this vector diagram that I already have going here, starting with the initial point. And I just want to see, if I start here and then graph vector d, do I end up down here? Are they equivalent? Well, let's see. So vector d goes down 1, 2, 3, 4, and to the left 1, 2, 3, 4. So let me go ahead and sketch that vector over here from this initial point, down 1, 2, 3, 4, left 1, 2, 3, 4, and it lines up. So yes, this is an equivalent statement. So vectors a plus 2b minus 4c are equivalent to vector d. And that's how we can do that. So these vectors, really, they can exist anywhere in space, right? So this blue line that I just drew is vector d. This black line over here that already existed, that is also vector d. They're the same exact vector. So we can move them anywhere in space, because all we really care about with the vector is how we travel along the vector, right? What is the magnitude? So what is the length of the line, and in which direction is it headed? Doesn't really matter where it starts and stops when we're talking about a single vector. Doesn't really matter where it starts and stops. It is equivalent anywhere you draw it, as long as the length is the same and the directions are the same. All right, so let's start to break down the details of the vector a little bit more and look at how do we describe it. So let's talk about vector components. So as it turns out, we've been talking about vector components this whole time when we talk about how we move along the vector. So now let's just formalize that definition. So we're going to be using 2 lowercase letters. So lowercase I is going to indicate horizontal movement along the vector. So lowercase I will be the horizontal component of the vector. And then we'll use lowercase j to describe the vertical component, or the vertical movement of the vector. Right? And these do not have numerical values at all. They're simply indicators. They're just saying that whatever number is attached to I is left-right movement. Whatever number is attached to j is up-down movement. So for example, here's a vector. This is vector v. And if we want to describe this vector, so vector v, we'll say vector v is equal to, and then we'll just look at, for positive or negative, are we moving left or right? In this case, we're moving to the right, and we're moving to the right by 1, 2, 3, 4, 5. So this is going to be 5i. And then for the j component, we're looking at, do we move up or down? In this case, we're going to move down 1, 2, 3. So this vector is going to be equal to 5i minus 3j. And again, I and j do not have any numerical value. It's just saying that since 5 is attached to I, we move to the right 5. Since negative 3 is attached to j, we move down 3. And that's just describing how to graph the vector. Sometimes, so this can be written in a variety of ways. So it can be written like this. There are some textbooks that will write it like this. So they'll use these kind of triangular brackets and call this 5, -3. And because the brackets are triangular, that's our indication that what we're looking at is actually a vector. So there's going to be some initial point. It doesn't tell us where the initial point is, right? And in fact, we're going to assume that the initial point is at 0, 0 at the origin. And then from there, we're going to move to the right 5 and down 3. So what I just said, so the initial, we assume that the initial point is going to be at 0, 0. That's what's called a position vector, right? So a position vector is defined as a vector with its initial point at the origin. So I'll write that down. It's a vector with its initial point at the origin at 0, 0. Right, so we might be given problems where we're told where the initial point of the vector is and where the terminal point of the vector is, and we'll be asked to describe it as a position vector. So here's an example. So this tells us that, or asks us to find the position vector v given an initial point of p at -1, 2 and a terminal point of q at 4, 6. So if we look at how to handle that, we'll say, okay, well, first let's graph the initial point at -1, 2. So here's the initial point P at -1, 2, and then the terminal point Q is at 4, 6. So is at 4, 6, so over here. And so if I graph this vector, it's just going to look something like this. So we'll connect, oops, I forgot to label the terminal point. There's terminal point Q. So we're going to connect the dots from P toward Q and write little arrows to indicate that that's the direction of travel of this vector. So there's our vector graphed. Now, in order to make this a position vector, we're just going to say vector v is equal to, and we want to find the I and the j. Right, so we want to find the I component and the j component. So we can do this one of two ways. We can either just count, so we can go over to the right 1, 2, 3, 4, 5. So 5i. And then count up to q, so up 1, 2, 3, 4. So that went up, so positive 4j, and there we go. There's the position vector, 5i plus 4j. So we could do it that way. We could also just look at the differences, right? So the difference in the x values of these coordinate points. So 4 minus -1 is 5, and the difference in the y values. So 6 minus 2 is 4. And that's how we can find our position vector. And all that means, if I was to graph the position vector, right, I'll do that in blue. So I'm going to go ahead and graph the position vector. It's just saying that we're going to put the initial point at 0, 0. And then from here, we're going to go to the right 5 and up 4. And it just makes it a little easier to graph, right? Because if the initial point is at 0, 0, we just go to 5 on the x-axis, 4 on the y-axis, boom, there's our vector, right? As opposed to it being out here in space. So that's what a position vector is. Okay, so that's cool looking at all the graph stuff. Let's talk about adding and subtracting vectors algebraically now. So if we're adding and subtracting vectors algebraically, we have those I and j components, and what we're going to do with those is we're just going to add the I components together and add the j components together, and that's going to give us our resultant vector. So for example, a very generic example, let's say that we have vector v, right, and vector v is going to be described with the following components. So very generic, just m representing any number, plus nj. So again, n representing any number. And then let's say that we also have vector w, and its components are going to generically be labeled oi plus pj, right? Again, where o and p can represent any number. Well, if we look at adding these vectors together, right? So let's say that we now want to find vector v plus vector w. We want to find what that's going to be. All we do is we add the I components together. So we'll have m plus o in parentheses, and then we're going to tag that with I. And then we're going to add the n and the p together in parentheses, so n plus p, and then tag that with the j component, and then there we go. Our vectors are added algebraically. Let's look at some examples. So here we're given vector v is 2i plus 3j, and vector w is 3i minus 4j. So we're going to do two things. So first we're going to go with, let's just add the two vectors together. So if we have v plus w, we're just going to look at it like this. So vector v plus vector w is going to be equal to, and I'll set it up like this because it can be the same process every time. So we can set it up like this. And now let's just put the I components inside this set of parentheses. So 2 plus 3, and the j components inside here. So 3 minus 4. And so then we can say that vector v plus w is equal to 5i minus j. Minus 1j, but we can just put minus j. So there we go. We added those two vectors together algebraically. If you were to graph this situation, you would come up with the same result. Now over here, we're going to both scale and subtract the vectors, and we're just going to let all the algebra do the work for us, right? So first thing I want to do maybe is let's find 2v, right? So we can do this in a couple steps. So 2v just means we're going to scale everything up by 2. So 2v is going to become 2 times 2 is 4i, and 2 times 3 is positive 6j, so there's 2v. And then I'm going to go ahead and apply the negative at the same time that I scale. So I'm going to multiply everything here by negative 3. So negative 3w is going to be equal to, so negative 3 times 3 is negative 9i, and then negative 3 times negative 4 is positive 12j. So I just let the math do all the hard work for me. And so now when I add these two vectors together, so if I do 2v minus 3w, I'll get 4 minus 9 is negative 5i, 6 plus 12 is positive 18j, and there's the resultant vector. So using the algebra to do it is fairly simple, right? We just let the algebra do the work for us. Cool. So that's how we do it algebraically. Let's talk about vector magnitude now. So sometimes we want to look at a vector and we want to observe its pieces individually, meaning we might want to analyze the magnitude of the vector all on its own, and then separately we might want to analyze the direction of the vector all on its own. So when we do that, we can indicate the magnitude of a vector with these two vertical lines. So let's say that we have vector v, for example. Well, the magnitude of the vector it's going to look like double absolute value bars. So this is magnitude of a vector. So this is the magnitude of vector v. Right, so just looking at the length of the line if we happen to be graphing the vector. Okay, so well, how do we find the magnitude of a vector? Well, let's look at an example for that, because I think that that's probably going to be the easiest way to go about this. Let's say that here's vector v, 3i plus 4j, and we want to know what the magnitude of this vector is. Well, if we think about this, right, so we're interested in the length of this line is the magnitude of the vector, right? So we want to find the length of the line. Well, thankfully, we're in an XY plane, horizontal and vertical lines, and if we just look at the components of the vector, it's going to be the clue for how to find the magnitude of the vector. So let's look at the I component. So this vector is wrong. Ooh, I need to fix that. I apologize. Let's get this out of the way. That's not right at all. This vector v, is actually 4i plus 3j. 4i plus 3j. Sorry about that. There we go. So this vector is 4i plus 3j. So let's look at the components of this vector. So the horizontal component is a length of 4, and the vertical length is a length of 3. The vertical component is a length of 3, and we can see that what happens there is we formed a right triangle, right? And if we have a right triangle and we know two of the sides, we can use Pythagorean theorem to find the missing side, right? So we can say in this case that 3 squared plus 4 squared equals the magnitude of the vector squared. And then we can just do the math here, right? So 9 plus 16 equals v squared. And then we put this together, we get 25 equals v squared, or magnitude squared. We take the square root of both sides and we get plus or minus 5 equals the magnitude of the vector. Now, this brings up an interesting discussion. Is it positive or is it negative? And it turns out the answer is that it will always be positive. So vector magnitude will always be positive. And the reason for that, so it'll always be positive. The reason for that, it kind of goes back to that first example I gave of the vector of if I'm traveling 2,500 miles from San Francisco due east or due west, the positives and negatives when it comes to vectors only indicate direction. Right? Positives and negatives indicate direction. There's no such thing as traveling negative 2,500 miles, right? I'm either traveling 2,500 miles to the east or 2,500 miles to the west. Either way I cut it, I'm traveling 2,500 miles, right? I don't know if planes have odometers, but I don't think they do. But you get what I'm saying, right? So it's only going to be positive magnitudes. Okay, cool. So let's see. Let's do a practice round. So here's vector W is 4i minus 2j, and what we want to do is find the magnitude of W. So go ahead and pause the video and see if you can find the magnitude of this vector on your own, and then we'll do it together. All right, so let's go ahead and do this together. So first thing I want to do is I just want to sketch the vector so that I have an idea of what's going on. I'm pretty visual, so that is helpful to me. If you want to jump in and just do the algebra, great. But I'm going to start by sketching vector W to the right 4 and down 2. So there's vector W, like that. And now to analyze the length of this vector, so I want to find the magnitude of W. And so to do that, I'm just going to lay out the components. So the first component goes to the right 4i, and the second component goes down, negative 2j. There's our right triangle, and now I can do some Pythagorean theorem. So 4 squared plus negative 2 squared equals the magnitude of W squared. And so we get 16 plus 4 equals the magnitude of W squared. So we have 20 equals W squared. We take the square root of both sides. We only want the positive value, so we get the square root of 20 equals the magnitude of W. And that's true, it is root 20, but we want to simplify this a little bit, so we'll get 2 root 5 equals the magnitude of W. And that's our final answer. That's the magnitude of W. So we might ask, what's the generic formula, right? So we can have a generic formula for finding the magnitude of any vector. So let's say that we'll go back to vector v, because that's a pretty common vector to have. So if we have vector v and we're trying to analyze the magnitude of the vector, we can say that it's just, we're going to kind of unpack the Pythagorean theorem a little bit. We'll say that this is equal to the square root of the I information squared. So we'll just say like x squared I plus y squared j. And notice that I put the I and the j outside of the parentheses because, again, I and j, we're not going to do any calculations with those. They're just there to label. So this is just indicating that this number is the horizontal component and that this number is the vertical component, but I'm not actually going to square I or square root j or anything like that. They're just indicators that follow along. So that's our general formula, is that the magnitude is equal to the square root of the x component squared plus the y component squared. All right, let's talk about a unit vector. So unit vector is useful because what we just did was we just observed the magnitude all on its own. A unit vector is how we can observe the direction of the vector all on its own. So a unit vector can be defined as a vector that is in the same direction as the vector that we're observing, but it only has a magnitude of 1. Let's make that make a little bit more sense. A unit vector is a vector that has a magnitude of 1. Let's start there. So it has a magnitude of 1. And it's a directional vector. That's its purpose, right? It's a directional vector. And let's break that down a little bit. So if a vector has a magnitude of 1, let's go back to the idea of a unit circle. Right, so if we go back to the idea of a unit circle, we know that the unit circle, right, the unit circle, it's a bad circle, but you get the idea. The unit circle has a radius of 1, right? So then if we superimpose this vector onto the unit circle, which has a magnitude of 1, we get the direction of that vector, right? So let's break this down a little bit. So let's say, for example, that we want to find a unit vector. Well, the formula that we can use to find a unit vector, and lowercase u with the little vector symbol is generally what we will use as the symbol for a unit vector. The way that we do that, so let's say that we have vector v, right, vector v, well, we can find its unit vector by just dividing the components of that vector by the magnitude of the vector. That's it. So we take the components of the vector, find the magnitude of the vector, and then divide those components by the magnitude, which is kind of a mouthful. So let's look at an example to make this make sense. So here we're given this example of vector v is 4i minus 3j, and we want to find a unit vector in the same direction as this. So first thing that I want to do is just sketch the vector, because I find it useful to have a visual. So I'm going to start right here, and I'm going to go 4i, so 4 to the right, minus 3j, so down 3, and there's my vector. So there's vector v, and I'll just go ahead and label this. This is vector v. All right, so now I want to find the unit vector in the same direction. So what I want to do then is, first of all, find the magnitude. So that's going to be our first step, is finding the magnitude of vector v. Well, the magnitude of vector v we know is going to be equal to the square root of the I component squared, so 4 squared, plus the j component squared, so negative 3 squared. Right, and so then the magnitude is going to be equal to, and you can shortcut this, but 16 plus 9, which is going to be 25. These Pythagorean triples are kind of nice to work with. So the magnitude of this vector is 5. All right, so the magnitude of vector v is 5. And so now to find the unit vector that's in the same direction as this vector, I'm just going to take the I component and divide it by the magnitude, so 4 over 5i, and the j component and divide it by the magnitude, so negative 3 over 5j, and there's our unit vector. Now you might ask, well, can we just call it 4 minus 3 over 5 I and j? But we don't really want to do that. We don't want to mix these things together, because like the whole point of labeling the vectors like this is that I is attached to the left-right information and j is attached to the up-down information. And if we kind of start to mix them together, it can get a little bit convoluted. So we do want to keep them as separate fractions. And then if we think about graphing this, right? So I'm going to graph vector u now, 4/5 I. So that's going to be, each one of these boxes is a length of 1. So I'm going to go about 4/5 of the way to the right. Let me actually get this tool over here. I'm going to go 4/5 of the way to the right, and then 3/5 of the way down. And if I get my cursor in the right spot, there we go. And so that vector is going to look something like this. So here's vector u, and I'll label that as vector u. And all that means is that this vector is traveling in the same direction as vector v, but it only has a length of 1. It has a magnitude of 1, which then allows us to describe the direction of the vector all on its own. All right, so let's dive into that a little bit further, how to describe the direction of a vector. So when we talk about direction angle of a vector, and let me back that up. When we talk about direction of a vector, there are a few different methods that we can use to describe directionality. Most of them break down, like come from unit circle measures, and then we interpret those in different ways. So more on that later. We're going to focus right now on how to describe the direction angle of a vector. And we just want to remember that when we work on the unit circle, if we're working in degrees, our unit circle goes from 0 degrees. That is our frame of reference, right? So every angle that we talk about on the unit circle is going to be in reference to this 0 degree angle on the right-hand side of the circle, right? So we have 0 degrees, 90 degrees, 180, 270, and then 360, right? So we just want to keep that in mind. All right, so let's look at an example to kind of lock this all together. So here we're given the vector v is negative 4i plus 4j, and we want to find the direction angle of the vector. So we want to describe in degrees what is the direction of this vector. So we'll start by sketching the vector. So vector v, negative 4i plus 4j, I'm going to draw out as a position vector. So from the origin, I'm going to go to the left 4 and then up 4. So there's our negative 4i, positive 4j. Let me just put arrows on both of these. And this is the method that I recommend that you use. There are a few ways to do this, but this method that I'm recommending right now is foolproof. It's fail-proof. It will work every single time, because it can be a little tricky, especially at first, to figure out where exactly we're working when we talk about angles. But this method will work every time. So first thing you do is graph the I component. That part's important. Graph the I component first, then graph the j component. And naturally, since one is horizontal and one is vertical, it's naturally going to form a right angle, right? So here's a right angle here. And then I want to graph the vector itself, right? So the vector itself goes from the origin out to the terminal point here. And so the vector itself looks like this. Right? And so when we do this, when we graph the components, I and j, and then we graph the vector itself, it's always going to form a right triangle. And now what we want to be aware of is when we're about to use a tool to solve for this angle, right? And our reference angle is always going to be the one that's connected to the origin. If we followed this method of first graph the I component, then graph the j component, then graph the vector, the angle that's attached to the origin is always going to be our angle of interest that we're solving for first. It's not necessarily going to be the direction angle of the vector, but it's going to be very useful in finding the direction angle. So I'll show you what I mean. Let's dive into this a little further. So I'm just going to label each of these points, or each of these components. So our I component is -4. So let me label that. And our j component is +4. And then we look at this and we go, okay, well, if I know two sides of this triangle and I want to find this missing reference angle over here, how do I do it? Well, here comes the tangent function, right? Because if this is our reference angle, now we have an opposite side and we have an adjacent side. So I'm just going to construct my mathematics like this. I'm going to say the tangent of theta, so the tangent of this missing angle, is equal to the opposite, in this case 4, over the adjacent, so -4. And so I'll simplify that. So I'm looking at the tangent of theta equals -1. Now, thankfully, this is something that's familiar to us on the unit circle, so we can solve for theta right away. Now, not all of the angles are going to be really nice and on the unit circle. A lot of times we're going to have to use a calculator to calculate this. So in order to calculate theta, right, that's the missing variable, I need to undo the tangent function that has it kind of trapped right now, right? So we're looking at the tangent of theta. We want to isolate theta. And the way to do that is with the inverse tangent key. So I'm going to go like this. I'm going to apply an inverse tangent to both sides. That's going to get rid of tangent on this side. And if I apply an inverse tangent on the right-hand side, inverse tangent is the key that looks like that, tangent to the -1 of -1. So I'm going to take the inverse tangent of -1. And what my calculator is going to tell me, that that angle is -45 degrees. Right, and it tells me that it's -45 degrees because the fraction was a negative, right? It was 4 over -4, which was -1. Now, what's important here is that you have the sketch, right? Because your calculator giving you an angle of -45 degrees, it doesn't know if you're in quadrant 2, which is where we are, or if you're in quadrant 4, right? Because, well, I'll show you that example in just a second. Okay, so what we need to do now is interpret this correctly. What this is actually telling us, we can kind of, if we have the sketch here, we can think about like just the absolute value of this angle and the fact that this angle that we just solved for, this one right here, that is 45 degrees, right? That's a 45-degree angle right there. Well, what we want to remember is that the angle that we're actually interested in is the one that is in reference to our 0-degree angle over here. Right, that's what we really care about is what is it in reference to 0 degrees? Well, that's over here, right? Our 0-degree angle is over here. So what we're really interested in is this angle, right? From the positive x-axis all the way over here, what is that angle? And so then we can say, oh, well, if halfway around the circle, if this is 180 degrees over here, then all we have to do is subtract 45 degrees from this, and we can see then that this is a 135-degree angle, and so that's how we can express that, right? So this direction, the direction angle of this vector is 135 degrees. So, well, I used theta to represent this interior angle, so I'll use alpha for this. And alpha is just a variable to represent an angle. So we can say that the angle of vector v is 135 degrees. Cool. And the thing I was talking about earlier, so we want to be careful because when we get to this point right here, the tangent of theta equals -1, and we're punching it into the calculator, we could have just as easily arrived at that situation if the vector, let's try vector w, if the vector is 4i minus 4j. Right, if we think about that scenario, let me just sketch that out real quick. 1, 2, 3, 4 to the right, 1, 2, 3, 4 down. So if we sketch that scenario, so I start with my I information first. So we go to the right 4, and let me label that as such. So that's the right 4. And then if we go down 4, so we'll go down 4 here. So there's our -4. And then we draw our resultant vector. So let's go ahead and draw the resultant vector here. Boom, there's that. And then we have our right angle right here. Whoops, have our right angle right here. And if we then our theta is attached to the origin, and if we start to solve this, we say that the tangent of theta is equal to the opposite, so -4 over the adjacent +4. We get ourselves into the exact same scenario where the tangent of theta is equal to -1, which is what we saw over here. So the calculator, again, is only going to spit out -45 degrees as our angle, but then we need to interpret that and say, oh, this is 45 degrees. Let me back that off of this is 360 degrees here, right? So if this is a -45 degree angle and this is 360 degrees here, then this is going to be 315 degrees all the way around, right? Let's see. Yeah, there we go. So this actual angle from 0, what is that? Oh, this actual angle from 0 over here, that's a 315 degree angle, right? So then the angle of this vector is 315 degrees. Hopefully that makes sense. Okay, moving on. Let's look at finding a vector given magnitude and direction. All right, so what we want to do with this strategy here, this is actually going to be one of the most useful ways that we observe vectors. So this is asking us to find a vector. And when it says find a vector, it means find the I and j components. So we're going to find a vector given the magnitude and the direction. And so we're going to have a very simple formula for this. We can say that a vector, so vector v, the I and j components, we can easily find that if we take the magnitude of the vector, so v in the absolute value bars, and we multiply that by the directional information, right? And if we think about how we find our I and j components, based on that last example where we were working with a unit vector on the unit circle, we know that horizontal values come from analyzing the cosine of whatever angle we're dealing with, and vertical values come from analyzing the sine of whatever angle we're dealing with. And so then here's our formula. Vector v can be written as the magnitude times the directional information. So let's look at an example to lock that into place. So let's say that a ball is thrown with an initial speed of 50 miles per hour at 30 degrees to the horizontal. So even if we start to just break this apart a little bit, when it says initial speed of 50 miles per hour, that's our magnitude component. So here's our magnitude. And then when it says 30 degrees to the horizontal, that's our directional information. Right, so here's our directional information. And so if we put those two things together and just sketch a little diagram of this, and the questions are this. We want to figure out what is the initial horizontal velocity and what is the initial vertical velocity, right? So we're gonna break it down into the components. So if we kind of sketch a diagram of this situation, right? So here's the horizontal, right? So our horizontal line just goes kind of like this, and then the ball is thrown at an angle of 30 degrees to that. So let me just sketch a line that's going to represent 30 degrees. So it's thrown kind of like this at this angle here. And the angle that we're looking at is 30 degrees. So here's a 30 degree angle. That says 30. Let me make that a little clearer. That's a 30 degree angle right there. And it's thrown with an initial speed of 50 miles per hour. So that's our magnitude. That's going to be the length of that line. Right, now what we want to know is what is the initial horizontal velocity and what is the initial vertical velocity. Well, thankfully, we can just use this formula right here. So we can write the vector. We can say that vector v can be represented by the magnitude, so 50 miles per hour, multiplied by the directional information, right? So we know that horizontal values can be analyzed by finding the cosine of, in this case, 30 degrees for I, and by the sine of 30 degrees for j. I kind of ran out of space there. Let me take that out. Sine of 30 degrees for j. Right, so then we'll just do this math. So vector v is equal to 50 times the cosine of 30 degrees is √3/2. So that'll be for I. And the sine of 30 degrees is 1/2. So that'll be 1/2 for j. And then we multiply this 50 in, so we'll get 25√3 for I and 25 j. So now we found the vector, right? The vector components are 25√3i plus 25j. And so then we can say the initial horizontal velocity is 25√3 miles per hour. And if we need to have an approximation, we can plug that into a calculator. And then the exact initial vertical velocity is 25 miles per hour. So if a ball is thrown at 50 miles per hour at a 30-degree angle to the horizontal, the initial vertical velocity, so just the part that's pushing it up, is 25 miles per hour. And the initial horizontal velocity, so the part that's pushing it toward the side over here, is 25 root 3 miles per hour. And that's how we solve that one. So that pretty much does it for all of the fundamental parts of vectors. In the next video, we will talk about applications of vectors. If you liked what you saw, please like and subscribe. And if you have any questions, go ahead and leave them in the comments, and I will do my best to answer the questions. Thank you so much.